Okay, so we're continuing our tour of different addition reactions to alkenes. In this case, we're going to look at acid-catalyzed hydration. In acid-catalyzed hydration, the components of water, meaning a hydrogen and an OH, are added to the pi bond. Now, acid-catalyzed hydration follows Markovnikov regioselectivity. So the hydrogen is added to the less substituted carbon, and the OH is added to the more substituted carbon. And the most typical catalyst used in acid-catalyzed hydration is sulfuric acid. And so very often when we have catalysts, we put those in brackets to denote them as catalysts. The mechanism for acid-catalyzed hydration is essentially the same as the mechanism for hydrohalogenation. In this case, we start off with a proton transfer. So the pi bond attacks the hydrogen on our acid, which in this case we're representing with H3O+. The hydrogen will end up on the less substituted carbon, so we end up with a carbocation on the more substituted carbon. Now water is acting as the nucleophile, and it attacks our carbocation. This produces an ion with a positive charge on the oxygen, and so we have one additional step that we didn't have in hydrohalogenation, where we have a water molecule that will deprotonate the oxonium ion. And then that results in our product. So the reactants and products of a hydration reaction are in equilibrium. And in fact, we saw in the last chapter that if I start with an alcohol, it's in the presence of an acid that we can have elimination to form the alkene. And so we need to know, how can we control whether we're going to force the reaction to the right to give us the addition products, or how to force the reaction to the left to give us the elimination products. And so to do that, we can use Le Chatelier's principle that we learned in Chem 1212. And that tells us that when we have a system in equilibrium, if we disrupt the equilibrium, the reaction will shift to try to reestablish equilibrium. And one of the ways that we can disrupt the reaction and cause the equilibrium to shift is by adding or taking away a reactant or a product. And if we add reactants, that will shift the equilibrium to the right. If we take a reactant away, it will shift the equilibrium to the left. And so if I want to favor the products, if I want to favor the addition products, then if I add more water, that will shift the equilibrium to the right, and I'll get the addition products. If I take the water away, that will shift the equilibrium to the left, and I'll get more of the elimination products. So if I want addition, I actually want to use dilute H2SO4, so adding more water. If I want to favor the elimination products, then I'll use concentrated sulfuric acid, meaning less H2O. So the stereochemistry of hydration reactions is very similar to the stereochemistry, and I'm sorry, this shouldn't say hydration, this should say hydrohalogenation. Right, and that is when we have a chirality center formed, because we have the carbocation intermediate, we're essentially going to get a 50-50 mixture of the R and S configurations. All right, so in this case, we want to predict the major product and draw the mechanism for the following reaction. So I know that we're doing hydration because I have an acid to catalyze it, and then because it's a dilute acid, I know I've got water present. And so my major product is going to be with the OH on the more substituted carbon and the hydrogen on the less substituted carbon. So my major product will be this. Now we want to check and see, am I going to get a mixture of enantiomers? But in this case, because I have a CH3 and a CH3, this carbon is not chiral, and so this will be the only product. It's not chiral. And if I want to look at the mechanism, So the first step is my pi bond is going to attack a proton from my acid. And I'll go ahead and draw the hydrogen in, even though I don't have to. The hydrogen will add here, meaning the carbocation will be here. In the next step, we have a nucleophilic attack by the water. And I have this oxonium ion. In the last step, I'll have another water molecule deprotonate our oxonium ion. And there we have acid catalyzed hydration.